All right. All right, you may begin.
All right. Hi, everyone. So my teammate Nachiket and me go to Berkeley, and we chose Phone a Friend on Earth instead of Martin, or instead of Mars. And then, so here's what our expressions were like when we saw the problem. Like, we didn't expect that it was so much CS coding. And then, so the problem is to find out, is to try to figure out what's good a rope phone is and to design a good rope phone. So which means that we need to define quality. So one way that we could define is to see how similar is it how similar the output is from the input waveform. And we specifically, we look at amplitude and frequency, in which my teammate is going to talk about later.
To talk about quality, we wanted to figure out how similar the output is to the input signal. So we thought of two ways to determine that. The first way was to actually physically compare the shape of the input waveform and the output waveform, and then calculate the variance between the two, which was normalized to be comparable across different experiments. And the qualitative measure we also thought of is the periodogram, which I shall explain in the next few slides. But first, we'll talk about variance. So yeah, most of you must have seen this in lab classes or in statistics or somewhere. It is just so at each point here, actually I have a very artistic depiction of this in the next slide. Yes, so imagine these are our two waveforms, and at each point on the x-axis, we find what the difference is between the two y values. We subtract them, and then we square them because we don't want any annoying negative signs there. And so we get this value, we add them up for all values of x, and we get one number, which I shall call the variance, although usually there is a division factor here, which we did not include. So this is how we calculated the variance, and we also divided it by the noise we got on the signal where there was no phone. So just like feeding the 441 hertz signal into the microphone. So with that, we were able to both account for the ambient noise as well as normalize our values so that we can compare every value for each experiment. The other quality measure we used was the periodogram, which I don't want to take too long here, but basically it is a graph where each peak tells us what frequency is present in the waveform. So if it is a pure sinusoid, we should expect just one sharp peak and everything else should be flat. So like a Dirac delta function, if you know what that is. But in practice, because of noise and because of experimental error, we usually have this spread at the base of this peak, so it looks more like a Gaussian. So for our experiment, we are going to use the width of this base as a measure of how much noise there was. And we'll ignore these secondary peaks because they were the results of experimental errors. This is just an example of another periodogram.
So here's our basic setup. So from top to bottom, we have paper cup, paper cone, paper cup, and then plastic cup. We tried to, it was actually my first time to try to assemble such a rope phone, and it was there were a lot of failure. Like my sister and I were trying to test whether sound was actually passing through. So after a lot of trying different materials, different strings and cups, we finally got something. Then, can you go to the next slide? Okay. So we're trying to figure out does the shape of the cup matter, and does the length of string matter? And with the great help of the YouTube, we were able to find videos that provide tutorials for us to use Python to convert audio file into sound wave graph.
So this is what we found from our analysis. What you see here is the raw waveform extended over a 1.5 second interval. So these two waveforms are for the same material of receiver, but for different lengths of strings. So as you can see, for the shorter string, we have a more consistent waveform with less beats, if you can call that. While for this one, the y-axis was cut off, but you would see that the amplitude is much smaller, and it's also very obvious that there are more beats, like there are more secondary pulsations to this. One possible reason, which we'll explore in the last slide, is that to increase the length of our string, we tied two strings together, which had a knot in the middle, which caused a discontinuity in the propagating medium. The other parameter we try to control for is the material and the shape of the receiver. So here we see the same length of string being used, but different receivers. And here it's blatantly obvious. For the cardboard cone, the amplitude is much smaller. It's almost like less than half of the amplitude for a paper cup receiver. So these are our observations, and we try to explain them using some theory. And for the periodogram, again, you can see that for the cone, we have more noise since the base of the Gaussian is wider, while for the plastic cup, we see that the base is much narrower. We try to explain this using some theory. So we have two observations, and both of them need to be explained. The first one is the fact that increasing the rope length would decrease the volume and introduce more noise in the system. So we explained that using the knot that we tied in the middle to tie the two strings together. This causes a discontinuity, which creates a new boundary condition. And this new boundary condition can cause refraction, reflection, transmission, which can complicate things and introduce additional overtones. And for the receiver type relation, which is that for the cone as compared to the plastic cup, we had much more noise. We utilize these two formulae, which you can see in front of you, which basically means that the attenuation is dependent on the coefficient of elasticity of the medium. So because of that, a cardboard cone has less elasticity, and therefore we expect it to have more attenuation. While for
unfortunately, your time is up.
Yeah, and we are also done.
Okay, nice.
Thank you, everyone.
It's lucky then. Okay, 4 minutes of questions begin now.